In this video, I'll be introducing a new topic of study about something called a vector. To begin, we'll be looking at how to define a vector and how to describe some of its characteristics. So we'll start with the formal definition of what a vector is. A vector is a directed line segment, and so it has two important components to pay attention to. There's both the length, which will sometimes be called the magnitude in a question, and there's the direction of it. So to describe these two components, the length and the direction, by length, I'm saying that the length of the line, the length of this arrow here, will matter. So if you see one going in the exact same direction or the same angle, but it's longer or shorter, we would describe that as a different vector. So the length of the line does matter. The second important component is the direction of it. So having a line pointing diagonally up and to the right would be different from a vector pointing diagonally up and to the left, or maybe pointing straight to the right or down. So the direction of it is also important, which will usually be described with an angle of rotation, just like the unit circle. Now for the standard notation of writing a vector. It's very similar to writing a coordinate like 2, 3, but for the vector, it'll have these pointed brackets on the sides instead. They kind of look like arrows. So if you see the pointed arrow, then we are talking about a vector that ends at this coordinate instead of just the coordinate itself. For example, you guys are familiar with writing a coordinate like 2, 3. That just means go right 2 units, up 3 units, and draw a dot at that location. So that would be the point 2, 3. Now we're learning that the vector 2, 3, so using the same numbers but changing it to the pointed brackets, means the directed line segment that starts from the origin and then it's going up to that coordinate. So it ended up going right 2 and up 3 total. And then we have an arrow on that side to indicate that it's going this way, not backwards. And another important piece of information we'll be dealing with for vectors in this first lesson is the magnitude of it, or, which I described up here, the length of the vector. This is often denoted by having the absolute value bars around the name of the vector. So if the vector is called vector v, then you put the absolute value bars around it, and that means we want to find the length of that line. So usually you could just measure it out if you had a ruler, for example. This formula should look familiar. This is basically just the distance formula. So if you have an x coordinate for the ending point and x coordinate for the starting point, it's the ending point minus the starting point for the x's squared, and then you add the ending point for the y and the starting point for the y squared, and you take the square root of that number. So this is basically just the Pythagorean theorem or the distance formula if you think of this as breaking it into the horizontal and the vertical pieces separately. If you are wondering why the distance formula is being used for the absolute value, that's because the formal definition of the absolute value is actually the distance from the origin. So now that we're in a two-dimensional space, we have an x value and a y value. To find the distance from the origin to a point, we use the distance formula. So you guys are more used to doing the absolute value bars for just the absolute value of -3, and that's because we're just defining how far is -3 from 0. It's a length of +3. But for two-dimensional, the absolute value bars indicate x and y distance combined, so the Pythagorean theorem or distance formula. So now we'll look at how to find the component form of a vector, and this is often referred to as the head minus tail rule. So if we don't have the information for the angle and the length of the vector, instead they've given us the location of the starting point and the ending point or the terminal point, then we need to be able to describe the vector in that component form. That's describing the horizontal and vertical motion. So the way we do that is we take the ending point and subtract the starting point for the x's, and then we repeat that process for the y's. So in this case, if I'm looking at the vector here, my ending location for x is 3, and my starting location for x was 0, and then I do a comma, and I do the same thing for the y's. So ending minus starting, so 4 minus 0, and then we can simplify this to describe it as the vector 3, 4. So when you are given the ordered pairs for the starting and ending position, you should be able to describe the motion of that by the vector component form, 3, 4, for example. Now, something interesting about vectors is that the starting and ending positions don't technically matter that much to us. What matters more to us is how far are we moving to the right and how far are we moving up, in this case, for example. So let's compare this to the other vector and see if they end up describing the same motion. So this second vector described over here, we see that we have a starting an ending x-coordinate. So the ending x-coordinate is -1, and then we're subtracting the starting x-coordinate. Now the double negatives are actually causing this to cancel, so since I'm subtracting a negative, it becomes +4. And then for the y's, I have my ending y-coordinate minus my starting y-coordinate. So if we simplify these numbers, we have -1 plus 4 is 3, and 6 minus 2 is 4. So what's important about this demonstration is that we got the exact same vector. So it doesn't matter that they started in different locations and end in different locations. Some questions may ask you, are they the same vector? And according to our component forms, we would say yes. What's happening here with the vectors is that we end up going to the right 3 and up 4. So the vectors are the same, even though they technically started from different positions and ended in different locations. So keep that in mind, that if you find the component form of two different vectors and they actually have the same numbers for the x and the y motion, then they are identical. So now for some more practice with finding the component form and the magnitude of given vectors. So here we can see that we have been given ordered pairs. One important thing to pay attention to is the fact that we have P to Q described, and you can see that there's an arrow indicating above it that we are starting from this point and ending at this point. So make sure you always follow the direction shown for the letters and the arrow on there, because it would have been different if we did the vector backwards. So in this case, now I know my terminal point and my initial point. So to find the component form, I'm going to have the x value for the ending and subtract the starting, but again, this is a double negative, so we'll end up adding 3. And then for the y's, the ending minus the initial. And then once we simplify this, we get -2, comma, -2. So you can probably imagine that this vector is describing something that from a location, it's going left and down. So you would expect a vector that's moving diagonally down and left combined. Next, we want to find the magnitude of this vector we just described. So the magnitude of the vector, and this is where we're just using the distance formula. Now, a nice thing to note here is that both the component form and the formula for finding the distance or the magnitude, it actually uses the same process of doing x2 minus x1. So since we already computed that number here, we can just go ahead and say that this is going to be -2 squared plus, and then the y values as well. We already did y2 minus y1. We already simplified that. So this also came out to -2 squared. And then we just want to keep simplifying what we have inside of the radical. So this is the square root of 4 plus 4. And always remember to simplify your radicals. Instead of writing square root of 8, you can always make a factor tree if you need help in breaking down the radicals. So the idea is that you're looking for two numbers that multiply together to equal 8. For example, 4 times 2. And then 2 is prime, so we don't need to break that down anymore. But 4 can be broken down more. 4 is equal to 2 times 2. So you keep going until all of the numbers at the bottom of your branches are prime values. And since I now have that, these are all prime numbers. Now we go through, and for a square root, we want 2 of a kind. So every time you see 2 of the same number, you can take that number outside the radical. Anything that doesn't have a 2 of a kind stays inside the radical. If there are multiple numbers coming out, multiply them together. If there are multiple numbers that don't have pairs, then they stay inside and get multiplied together as well. So in this case, I have a 2 come out and another 2 stay inside. This answer would be 2 root 2. So that's the length of the vector if we plot it out starting from the origin and then measuring left 2 down 2. Then the distance of that diagonal line is 2 root 2. Here's a second example. So we'll begin with the component form again. So I need to do the ending minus the starting points. So for the x's, 3 minus -2. And for the y's, 4 minus 2. So when you simplify this one, we get a vector 5, comma 2. So this vector seems to be going diagonally up and right because it has a positive x and a positive y. It's going more to the right than it is up and down though. So I would expect a vector that's doing something like this. And then for the second part, the magnitude of this vector, again, we've already computed what the x2 minus x1 and y2 minus y1 parts are, so we can just go ahead and use those already simplified numbers. So we end up with 5 squared plus 2 squared. It wasn't as important to use parentheses on this one because I didn't have a negative number that I was squaring. So whether I wrote parentheses around the 5 and squared it wasn't going to change my answer. It didn't matter more the negative number because if you don't use the parentheses, then you actually end up with a negative answer if you don't have parentheses around the negative. So now to simplify this a little bit further, we have 5 squared, which is 25, and 2 squared, which is 4. Now the problem with this square root is that 29 cannot actually be broken down. If you make a factor tree, we don't have any numbers that we can get 2 of a kind from if we're reducing or simplifying the square root of 29. So this number does have a decimal value if you type it into your calculator. It should be a little bit bigger than 5, but it's going to be less than 6. So I know that this line, this diagonal vector, is approximately 5 point something. And that's the magnitude of the vector. So that's it for the notes. Hopefully you guys will feel comfortable with finding both the component form to describe a vector's motion and finding the magnitude or the length of the vector.